Here's a video to help with converting between moles and grams. So the question says to convert the amount of moles below to grams. So first, we'll convert 0.00267 moles of arsenic to grams. Now that's the lethal dose of arsenic. And so every time you want to do a conversion, you want to identify the units they're asking for and the numbers they're giving you. Here, the units they're asking for are grams of arsenic. And the number they give you is 0.00267 moles of arsenic. So in order to do the conversion, we need to know how those two units relate. How do moles of arsenic relate to grams of arsenic? And that you get from the periodic table. So 1 mole of arsenic would weigh, you go to the box on the periodic table, and the box should always have at least 3 things. You'll have the symbol in the middle, a number on top, and a number on bottom. The number on the bottom is the number of grams in 1 mole. So if you had 1 mole of arsenic, 6.022 times 10 to the 23rd atoms of arsenic, and you put that on a balance, how much would it weigh? It would weigh 74.922 grams. And those numbers on the bottom, you can round if they're really close to the nearest number. So here, 1 mole of arsenic would weigh 74.922 grams. Here I'm just going to put 75. All right, so now that we have that conversion factor, we can take the number they give us, which is 0.00267 moles of arsenic. Every time you do a conversion, write a multiplication sign, a fraction bar, and the units you start with go on the bottom of the fraction so that they'll cancel out. Here, that's moles of arsenic. Then we fill the fraction in with our conversion factor. Next to moles of arsenic, we'll go the number 1, going over the fraction bars like going across the equal sign, and on top you'd have 75 grams of arsenic. So moles of arsenic cancels out, we're left with grams of arsenic, and if you plug this in a calculator, you'd put 0.00267 times 75, then hit enter, divided by 1, enter, and you'd get 0.2 grams of arsenic. And that is how many grams of arsenic you would need, or that you would have for to be a lethal dose. All right, next. They want us to find the grams in 0.048 moles of copper. And that's about the amount of copper that was in pennies before 1982. After 1982, they made the inside of a penny zinc, and they only put copper on the outside. These days, it costs more to make a penny than a penny is worth in terms of the metal that makes it up. All right, so the unit they want is grams of copper, and the number they're giving you is 0.048 moles of copper. So that's what we have to work with. In order to do a conversion between those two units, we need to know how they relate. So how do moles of copper relate to grams of copper? Well, 1 mole equals, and the grams in 1 mole we'll get from the periodic table. You can see where copper is, and if you go to the box where it is, you'll see that number on the bottom, 63.546, that's the number of grams in 1 mole of copper. So if I had 1 mole of copper, 6.022 times 10 to the 23rd atoms of copper, and I put that on a scale, it would weigh 63.546 grams. So I'm going to just round that to 63.5. Now that gives us our conversion factor. So now we can take the number they give us, 0.048 moles of copper. Every time you do a conversion, write a multiplication sign, a fraction bar, and the units you start with, here moles of copper, go on the bottom of the fraction so that they'll cancel out. And then you fill the fraction in with the conversion factor. So next to moles of copper goes the number 1, going over the fraction bars like going across the equal sign, and on top you'll have 63.5 grams of copper. Moles of copper cancels out, and we are left with grams of copper. And if you plug this in a calculator, you'd put 0.048 times 63.5, enter, divided by 1, enter, and you should get 3.048 grams of copper. So about 3 grams of copper in a single penny before 1982. Copper is a useful metal. It conducts electricity very well, so they use it for wires. You can see what it looks like, just raw out of the ground in the bottom right here. It also doesn't corrode very much, so they like to use it for pipes and for cooking pots. But one thing that does make it corrode is if it's exposed to very salty water or sometimes very acidic, very salty air or water or very acidic air or water, then it will sort of oxidize and it turns from that brown, golden, coppery color to that pale, dull green color. The Statue of Liberty is actually made of copper. It's just oxidized, so it turned that light green. All right, now it asks us to convert each amount of moles to grams. So what units are they asking for? Grams. They want grams of magnesium chloride, MgCl2. And what do they give us? They give us 2.29 moles of MgCl2. So those are our units. We have to do the conversion. In order to do that conversion, we need to know how those two units relate. How do moles of MgCl2, magnesium chloride, relate to grams of MgCl2, magnesium chloride? Okay, now in this one, we don't just have a single element. We have a compound that's made up of a couple elements and a few atoms. So we're going to keep track of this by writing them separately. We've got magnesium and we've got chlorine. In the compound, we only have one magnesium atom. Now, a mole of each magnesium atom would weigh 24.305 grams. So each mole of magnesium is going to weigh 24 grams. And since we only have one of the magnesiums, it'll be 24 grams coming from magnesium. In the compound, we have two, you can see it in the bottom, two chlorines. Each mole of chlorine will weigh, that number on the bottom in the box in the periodic table, 35.45 grams of chlorine. So I'll put 35.45. And since we have two of them, altogether that's 70.9. 2 times 35.45. Okay, so each mole of MgCl2 has 24 grams coming from the magnesium and 70.9 grams coming from the chlorines. Altogether, that is 94.9 grams. So there are 94.9 grams of magnesium chloride in every 1 mole of magnesium chloride. So that gives us our conversion factor. Now that we have our conversion factor, we can take the number they give us, that's 2.29 moles of magnesium chloride. Every time you do a conversion, write a multiplication sign, a fraction bar, and the units you start with here, moles of magnesium, go on the bottom of the fraction because you want it to cancel out. And we're going to fill that fraction in with our conversion factor. So next to moles of magnesium chloride goes the number 1, going over the fraction bars like going across the equal sign, and on top you'll have 94.9 grams of magnesium chloride. Moles of magnesium chloride cancel out, and we're left with grams of magnesium chloride. So if you punch this in a calculator, it'd be 2.29 times 94.9, enter, divided by 1, enter, you should get something like 217.32 grams of magnesium chloride. So 2.29 moles of magnesium chloride would weigh 217.32 grams of magnesium chloride. So if you take magnesium, and magnesium is the metal that's in those handheld pencil sharpeners, and you mix it with chlorine, usually a toxic yellow-green gas. Here they've condensed it into a liquid. In just the right way, it'll make this magnesium chloride. You can see a clump of it at the bottom right there. And one use of that is to put in compresses that nurses would press to the joints, the inflamed joints of people who have arthritis, to help relieve the pain. And in that form, it's called bisulfite. It's a mineral in the ground. All right, here it says convert each amount of moles to grams, and they give us 0.678 moles of phenol, C6H6O. So what units are they asking for? Grams of phenol, C6H6O. And what number do they give us? 0.678 moles of phenol, C6H6O. So it's a conversion, and in order to do the conversion, we need a conversion factor that relates those two units. So how do moles of phenol, C6H6O, relate to grams of phenol, C6H6O? Now again, we have more than one element here, so we have to keep track of the weights coming from each element separately, and then we'll add them all up. Now let's assume we have 1 mole of phenol. That means we would have we have carbon, hydrogen, and oxygen. We're going to keep track of these things separately. If we have 1 mole of phenol, that means we have 6 moles of carbon. If you go to the box in the periodic table, you'd see that each mole of carbon weighs around 12 grams. So 1 mole of carbon weighs 12 grams. In this compound, we'd have 6. So altogether, that would be 6 times 12, 72 grams coming from carbon. You can see in this compound, if we had 1 mole of this compound, we would have, you can see the number at the bottom there, 6 moles of hydrogen. Then you can go to the periodic table, you look at the number below the symbol, and you can see that 1 mole of hydrogen would weigh 1 gram. Since we have 6, it would weigh 6 times 1, or 6 grams. In this compound, if we had 1 mole of this compound, we'd only have 1 mole of oxygen. Oxygen doesn't have that subscript there at the bottom right, which means you just have 1 of them. If you go to the periodic table, you look at the bottom of the box, the number there, it's around 15.999 or 16 grams in 1 mole. So here, altogether, we'd have 1 times 16 equals 16 grams coming from oxygen. So if we had 1 mole of phenol, we'd have 72 grams coming from carbon, 6 grams coming from hydrogen, and 16 grams coming from oxygen. Altogether, that's 94 grams. So there are 94 grams of phenol in 1 mole of phenol. All right, now that we have that conversion factor, we can take the number they give us. Every time you do a conversion, write a multiplication sign, a fraction bar, and the units you start with go on the bottom of the fraction so that they cancel out. Now I'm going to fill that fraction in with my conversion factor. Next to moles of C6H6O goes the number 1. Going over the fraction bar is like going across the equal sign, and on top you'll have 94 grams of C6H6O, or phenol. Moles of phenol cancel, and we are left with grams of phenol. If you plug this in a calculator, you get 0.678 times 94, then hit enter, divided by 1, enter, you should get something like 63.732 grams of phenol. And that's how many grams it would weigh if you had 0.678 moles of phenol. So if you took carbon, which is sometimes coal or sometimes diamond or sometimes the graphite, like in pencils, depending on how you squeeze it together, and you mix it together with hydrogen, which makes up those beautiful clouds in outer space, and we'll also mix it together with oxygen. Here you can see liquid oxygen, which is magnetic, so it sticks to magnets. And you mix it together all in the right way, you would get phenol, which is this compound on the right here. And phenol was the original antiseptic that was used in Listerine. It killed bacterial cells really well. Unfortunately, it also killed human cells pretty well too. So people would get throat cancer because of the original Listerine. So they replaced it. It's not in Listerine anymore. But they still do use it in very, very small quantities as a preservative in some vaccines, not in all of them. And it also helps to treat ingrown nails. All right, more problems. So here, they ask us to convert each amount of grams below to moles. And so they give us 1,150 grams of titanium. It's about the amount of titanium in a bicycle frame that was made of titanium. So it's a conversion problem. And for every conversion problem, you want to ask what units are they asking for and what number are they giving you. The units they're asking for are moles. So we are trying to find moles of titanium. And the number they're giving us is 1,150 grams of titanium. Okay. In order to do this conversion, we need a conversion factor that relates those two units. How do grams of titanium relate to moles of titanium? And we can get that number, that relationship from the periodic table. If you go to the periodic table, you look at the box that has titanium, you can see that below the symbol there, below the TI, you have 47.867. That's the number of grams in 1 mole of titanium. So 1 mole of titanium equals around 48 grams. All right, now that we have that conversion factor, we can take the number they give us, which is 1,150 grams of titanium. Every time you do a conversion, write a multiplication sign, a fraction bar, and the units you start with. Here, grams of titanium go on the bottom of the fraction because you want them to cancel out. And then you fill that fraction in with your conversion factor. Next to grams of titanium goes 48. Going over the fraction bar is like going across the equal sign, and on top, you'll have 1 mole of titanium. Grams of titanium cancel out, and you're left with moles of titanium. The way you'd plug this in a calculator, you'd have 1,150 times 1, then hit enter, divided by 48, then hit enter. You should get something like 23.56 moles of titanium. So if you had 1,150 grams of titanium, you would also have 23.56 moles of titanium. That's about the number of moles of titanium in a bicycle frame. Now, titanium is a really interesting metal. It's lighter than aluminum, but stronger than steel. So it's an expensive metal, but they use it for a lot of athletic products, things that where weight is very important and strength is also very important. So bicycles or tennis rackets. Also for things like crutches or wheelchairs, again, where weight is important and strength is important, or for the fans in airplane, or the blades in airplanes, also where weight is important. It is a very strong metal. It doesn't degrade very easily, and it's inert in the human body, so they use it for implants to replace different joints or things you might have lost, whether teeth or hip. And also, it doesn't rust, so it's really useful for, titanium is really useful for especially nautical things, where if you're out in the ocean a lot and you're using iron, it would rust, or a lot of metals corrode, but titanium wouldn't, so it's really useful to use for, say, fish hooks or fishing line or a diver's watch, things like that. All right, let's convert each amount of grams to moles. Now here they give us 0.200 grams of osmium. You can see a picture of osmium in the bottom right. So what are the units they're asking for? Moles of osmium. What number are they giving us? 0.2 grams of osmium. So now, in order to do the conversion, we need a conversion factor that relates those two units. How do grams of osmium relate to moles of osmium? And to get that, we'll look at the periodic table. Osmium's there on the periodic table. If you zoom in on that box, you can see the number below the symbol, 190.23. That's the number of grams in 1 mole of osmium. So there are 190 grams in 1 mole of osmium. If you took 1 mole of osmium, that's 6.022 times 10 to the 23rd atoms of osmium. You put them on a scale, it would weigh about 190 grams. All right, so once we have that conversion factor, we can take the number they give us, 0.200 grams of osmium. Every time you do a conversion, you write a multiplication sign, a fraction bar, and the units you start with go on the bottom of the fraction so that they cancel out. Here, that's grams of osmium. Now we're going to fill that fraction in with our conversion factor. Next to grams of osmium goes 190, going over the fraction bars like going across the equal sign, and on top we'll have 1 mole of osmium. Grams of osmium cancel out, and we are left with moles of osmium. If you punch this in a calculator, you'd have 0.200 times 1, then hit enter, divided by 190, then hit enter. You should get something like 0.0011 moles of osmium. That's how many moles of osmium you'd have if you had 0.2 grams of osmium. Osmium is a really hard metal. The problem is, though, it's also pretty toxic. So what they do is they alloy it with other metals to make the other metals harder. So it adds resistance to things that are scratched or pressed against other things a lot. For example, the connections in an electrical outlet, or the ends of a pen, a fountain pen. It's also the densest of the elements. It's about 22.5 grams in every 1 milliliter. Water is 1 gram per milliliter, so it's 22 times more dense than water. There's also a compound called osmium tetroxide, and it looks like this. Believe it or not, that metal that we saw before is inside of this compound, and it's really useful in organic chemistry. You'll hear of it if you take an organic chemistry class. There's a reaction that people developed for it that won the Nobel Prize in 2001 using this osmium tetroxide, which is a derivative of that metal osmium. All right, how about this? It's asking us to convert 47.3 grams of NH3, which is ammonia, to moles. Now that's about the amount of ammonia that you'd have in a bottle of Windex. Okay, so how many moles of ammonia are in a bottle of Windex? Windex is a mixture, it doesn't just have ammonia, but that's about how much ammonia would be there. So what units are they asking for? Moles of ammonia. And what number do they give us? 47.3 grams of ammonia, NH3. So we need a conversion factor that relates those two units. How do grams of NH3 relate to moles of NH3, or ammonia? And to do that, we're going to use the periodic table. Now we have more than one element here, so we're going to think about each of them separately. We have nitrogen and we have hydrogen. Now let's say we had 1 mole of ammonia. In that case, we would also have 1 mole of nitrogen. For every 1 mole of this whole thing, you'll have 1 mole of nitrogen, because there's no subscript below the N. So 1 mole of nitrogen. And we can go to the periodic table, look at the number at the bottom of the box for nitrogen, and see that each mole of nitrogen would weigh 14 grams. So 14 there. So since we have 1 mole of nitrogen in this compound, altogether that would be 14 grams coming from the nitrogen. All right, how about hydrogen? In this compound, if we had 1 mole of this compound, we would have 3 moles of hydrogen. We can go to the periodic table, look at the number underneath the symbol, at the bottom of the box, and we have around 1 gram for each mole of nitrogen. Since we have 3, altogether that's going to be 3 times 1, so 3 grams coming from hydrogen in this molecule. So in 1 mole of this compound, we have 14 grams coming from nitrogen, 3 grams coming from the hydrogens. Altogether, that is 17 grams. There are 17 grams of NH3 in every 1 mole of NH3. So that gives us our conversion factor. Now we can take the number they give us, 47.3 grams of NH3, write a multiplication sign, fraction bar, and put the units that we start with on the bottom of the fraction so that they'll cancel out. And we're going to fill that fraction in with the conversion factor. Next to grams of NH3 goes the number 17. Going over the fraction bar is like going across the equal sign, and on top you'll have 1 mole of NH3, or ammonia. Grams of ammonia cancel out, and we are left with moles of ammonia. And the way you'd plug this in a calculator would be 47.3 times 1, enter, divided by 17, enter, and you'd have 2.78 moles of NH3, or ammonia, in every in a 32 fluid ounce bottle of Windex. So if you took nitrogen, which is this clear gas, and it's also a clear liquid when it's cold enough, it makes up 79% of the atmosphere and the air that you're breathing right now. You take that nitrogen, you mix it with hydrogen, which is the gas clouds in outer space again, and you put it in just the right way, you make ammonia. All right, now let's convert the amount of grams of this isopropyl alcohol to moles. Isopropyl alcohol is rubbing alcohol. You use it to disinfect wounds. So, what units are they asking for? Moles of isopropyl alcohol, C3 H20. What number are they giving us? 0.488 grams of isopropyl alcohol, C3 H20. So in order to do that conversion, we need a conversion factor that relates those two units. How do grams of C3 H20 relate to moles of C3 H20? Okay, well we have more than one element here, so we're going to think about each of them separately. We have carbon, we have hydrogen, and we have oxygen. Now let's say we had 1 mole of this compound. If we had 1 mole of this whole thing, we would have 3 moles of carbon. And if we go to the periodic table, you can see there's carbon. The number at the bottom tells us how many grams 1 mole would weigh. So each mole of carbon would weigh 12 grams. Since we have 3 of them, that adds up to 3 times 12, or 36 grams coming from carbon. All right, hydrogen. If we had 1 mole of this whole compound, we would have 8 moles of hydrogen. We can go to the periodic table, look at the box, the number underneath the symbol is 1. Each mole of hydrogen weighs 1 gram. So we can plug that there. Since we have 8 grams in this compound, altogether it's 8 times 1, or 8 grams coming from hydrogen. And if we had 1 mole of this whole compound, we'd only have 1 mole of oxygen. There's no subscript at the bottom right of that O, so that means we just have 1. If you go to the periodic table, look at the box, the number underneath the symbol, each mole of oxygen weighs around 16 grams, 15.999. So 16 grams. Since we have only 1 in this compound, altogether it'd be 1 times 16, or 16 grams coming from oxygen. Okay, so if we had 1 mole of this C3H8O, we'd have 36 grams coming from carbon, 8 grams coming from hydrogen, 16 grams coming from oxygen. Altogether, that is 60 grams. So there would be 60 grams of C3H8O in every 1 mole of C3H8O. And again, that name for that is isopropyl alcohol. All right, so once we have that conversion factor, we can take the number they give us, that's 0.488 grams of isopropyl alcohol. Every time you do a conversion, write a multiplication sign, a fraction bar, and the units you start with here, grams of C3H8O, go on the bottom of the fraction, because you want them to cancel out. And I'm going to fill that fraction in with my conversion factor. Next to grams of C3H8O goes the number 60. Going over the fraction bars like going across the equal sign, and on top you'll have 1 mole of isopropyl alcohol. Grams of isopropyl alcohol cancel out, and we're left with moles of isopropyl alcohol. Now if you plug this into a calculator, you'll get 0.488 times 1, enter, divided by 60, enter, and that's 0.008 moles of isopropyl alcohol. It's about how much would be in a 16-ounce bottle of rubbing alcohol that you'd get at CVS or Walgreens. So if you take carbon, which again could either be coal or the graphite in a pencil or diamonds, depending on how you squish it together, and you react it with hydrogen, gas clouds in outer space, and oxygen, here you can see a picture of solid oxygen, very, very cold. Yeah, react it in just the right way, you'll get this rubbing alcohol. Thanks so much for your attention.